Okay, it's me, Mario.
What is x to the power of 4?
Should have skipped.
Okay, so this is kind of the essence behind index laws. An index is like an exponent or a power. And so there's a little bit of a difference between how we write things, whether you're connecting things in one way or connecting numbers in another. 4 times 3 really means what?
12.
Yes. Yes.
4 plus 3 plus 4. No, 4 plus 4 plus 4.
4 plus 4 plus 4. I like that. If we're doing it in terms of threes, it's
3 plus 3 plus.
cool. This means 4 of these things. So this is 4 of these. How are they connected?
Plus.
Yeah, I don't know. You're right that it's the same thing as 3 4s. But I'm just going to take this inner parenthesis as the thing that we're using. And this is the number of times they're added. So 4 times x would be x plus x plus x plus x. Right? This is fairly obvious. But the hard part comes in when you start mixing and matching things, keeping track of what operation am I doing with all of these. So this 4 cubed is really, actually I want this, sorry. I want 3 to the 4th, switched it up. 3 to the 4th really means what?
3 times 3 times 3?
Yeah, the same thing. There's 4 3s. The only difference is that these are being multiplied, right? And this is the same thing. I got x's being multiplied. How many of them are 4? So we use this thing in front. This is called the coefficient. When we're talking about how many are added together. But we don't want to just add and subtract all our life. So we use this thing, which is called an index. If you're British, or a exponent, or power sometimes, right? When you're talking about multiplication. Multiplication. Right? Fairly straightforward, but this is a tripping point. People are like, oh, what am I adding, multiplying? And so, like, just keeping track of this is adding, this is multiplying. I think that'll make what's coming up next more approachable. Cool? Great. Let's jump in. So, there's just a bunch of examples, and we can like talk about the index laws all we want, but I'm just going to run you through like a bunch of examples. Follow with me with most of them. I'll do one, have you do one, etc., etc. But this is kind of the one of the basics is like that we can write as a prime factorization. Like so I don't know. Think about 50. 50 you could write as 10 times 5. But that's not, like 10 is not as basic as it could be. This is a prime number, but you could turn 10 into 2 and 5. And each of those are now prime numbers, so you could call 50 times 5 times 5, right? We've done this for factoring and such. So, no surprise, you could do that same thing here. I don't know the prime factorization of that. So I'm just going to start breaking things off that I see, like x divided by 2, right? So start with that. See if you can break it into its prime factorization of just like prime numbers multiplied together like that. Right? See if you can mess with that a little bit. If you're not sure what to do, divide by 2. See what happens. Welcome to use your calculator if you want. At this point. That's probably what I'd do with it, is make this like factor tree and just think about dividing, right? This is divisible by 2, bam. This ends in a 2, so it should be divisible by 2, ends in an even number, should be divisible by 2. They're not, so like I tried 3 again, and so now this is the list of prime numbers that when multiplied together give you 504. And so we could call 504 in its most basic sense a 2, and a 2, and a 3, and a 3, and a 3, and a 7, right? There's a little bit nicer way to write that out. What do you think, George?
Wait, on the left it says you can divide by 2 3 times, and then by 3 twice.
Yeah. Oh, thanks. Yeah.
Shazam. Shazam.
What's a nicer way to write that instead of like 2 times 2?
2 cubed, 3 squared.
Yeah. Yeah, I got 3 of these, so 2 cubed. We use a superscript, the cube, to say that these have been multiplied. If they were added together, you'd say 3 times 2, but they're not being added, they're being multiplied. And then 3 squared, and then 7. So you might say that that's the prime factors, kind of in a simplified form. We're going to play with these, the index, and how we can combine them, rip them apart, put them together. That's kind of our focus today. Right? Okay. A little bit of a fussy business. I'll do one with you. The little bit of a fussy business, especially when you put it in the calculator, is where the parentheses are. Because if you say negative 3 squared in your calculator, it thinks you mean negative 1 times 3 times 3. And this is 9 times negative 1 is negative 9. If you do this, it means negative 3 times itself, which is positive 9. So you got to be careful with the parentheses. So with this, I'm going to do the same thing. This is, it always is a little bit slower to write it out, but it will always help you, right? So negative 3 times negative 3 times negative 3 times negative 3. That's what negative 3 to the 4th means, right? 4 of them. That's a positive 9. That's a positive 9. That's a positive 8. Cool. You try these. Slight differences, right? Where the parentheses are, where the parentheses aren't. Think about that. Notice the effects of the brackets. I think somebody else was up there. Yeah, she was up there. I thought he was more interesting. Handsome guy. He actually was a math teacher. Weird. It's weird.
What does that say? Is that 3 to the 5 or 3 to the 3?
3 to 5? 3 to 5? What different parentheses around? So negative 3 to the 4th really means negative 3 to the 4th. Right? Be careful with that. They look very similar, right? But if you punch one into your calculator and the other, they'll give you different things. This means I have negative all of this junk. All of this junk is 9 and another 9, that's 81, and then negative that, negative 81. Similarly, what's 81 times 3?
243.
243, thanks. So this means negative 3 times itself 5 times. Regardless of what value that is, can you tell me about the sign on it?
Negative.
Yeah, right? That's going to be positive, positive, 2 positives multiply positive, and then you multiply it with a negative, negative. So whatever it is, I know it's going to be negative. And they said 243. Shazam. Right? Probably, I know you could do that multiplication in your head if I gave you enough time, but like, that's not our focus, is like multiplying big numbers together. But, so there you go, bam. This is a little bit fussy. So this is still this. So we don't really have to do anything else. It's that number and then negative. So this would just be positive 243. Cool? Just be careful for the parentheses. Notice the effects of the brackets. I'm recording this. I probably should. All right. Try it with your calculator. Make sure you can do it. Try these two. Try that one and that one. Throw them in your calculator. Make sure you get these on the bottom. Yeah, just so you can. I want you to be able to check everything with your calculator. What? For shame. Oh. There's a caret on the side, right below clear. Yeah, Smart View takes a while. Big button that says clear.
Oh, yeah.
Wait, why do you get given the answer for?
Because I want you to be able to check it.
Oh, okay.
Just make sure you got it.
Yeah.
It's not supposed to be a surprise. I just want you to make sure you can do it. As my TI warms up, I'll show you where this is. But if you haven't found this, it's under the clear button.
Yeah, but you have to write the number.
Also, like your parentheses
Like
are
if
going
you
to be
write
important.
5 now, it's going to fill the thing with 5.
Yeah, you see like that little
Okay.
caret thing
Ah.
under the clear button. Cool. So you're okay with those? You got those values up? Shazam and Shazam. Be careful with your parentheses.
Anyways. It's 5, 15, 16.
Oh, no. Now calculator wants to fire up. Oh, look at that. Natural log of 7 divided by natural log of 3. We'll get there soon enough. So if you say negative 5 to the 6th, it gives you that, right? And that's because that's like 5 to the 6th is positive because it's positive 5s multiplied together. And then you slap the negative on it afterwards. And that's different than negative 5 a bunch of times. Like every 2 sets of negative 5s, you get a positive, a positive, a positive. So that thing should be positive. So the brackets do matter. Be careful with them. Cool? So I just used this button. Zoom! All right. Now, we want to be able to check things on our calculator. But we're not just going to like carry that thing around for the rest of our mathematical lives. So I want to also be able to calculate things by hand. Oh my gosh. And there's a couple of these index. I feel like that some days. There's a couple of these, what they call index laws. And this is one of them. Write that down in that format, and I'll show you like why that makes sense. And then we'll try a problem with it. Index law number 1. It's not really called index law number 1. I'm just making stuff up. But okay, so here's the fussy business behind there. when you're not sure, or when you're moving fast, right? When I'm doing like my brain's on trigonometry and then all of a sudden I'm blasted with something like this, I'll just stop and like check myself that I'm not making up mathematics. Like this. If you have 2's and I have 3 of them there, and I'm multiplying 2 to the 4th, I'd like to squish them together. 2 to the 3rd really is 2 times 2 times 2. And this is 4 of them, 2 times 2 times 2 times 2. And they're being multiplied together. So instead of just saying 2 times 2 times 2 times 2 times 2 times 2 times 2, just like crunch those together and call it 2 to the 7. Because I've got 3 there and 4 more there. Everybody's being multiplied. So you can call it 7, which is really 2 to the 3 plus 4. Sitting by itself is pretty obvious, right? But the hard part comes when you're like doing a lot of different mathematics, and then you have to think about, oh yeah, how do I combine those? That's when it gets sticky. So practice and like make sure it makes sense to you. This does not work if you have this. Oh, I want that back. I didn't mean what I said. If you have this, 2 cubed plus 2 to the 4, because it's 2 times 2 times 2 plus 2 times 2. This plus breaks up the multiplication rhythm. And when you use an exponent, it means only multiplication. So you have to leave this as this. You can't, maybe you could simplify it by saying, let's factor out a 2 cubed, and what's left over is 1 and a single 2. It's like you pull 3 of these 2's out and 3 of these 2's out. You're left with a 1 to place hold there and this lonely 2. You could do something like that, right? So take those ideas and try these in the room. Squish them. Those two, B and C. So the first one, you have bunches of A's. You have 4 there multiplied, and then multiplied by 5 more. So you should have 9 multiplied. Not a big deal, right? And then this one, I've got 4 X's and then some more X's. How many? I don't know. A X's. And so you can leave it as X plus 4A, which simplifies to X to the 4 plus A. Right? I can't simplify it. If you tell me A, I'll put it in, but I don't know it. So you gotta leave it. Cool? Similarly, here's our exponent law number 2. Jot that down. I'll show you what it means. Your index law. Go with the British.
The Americans call it.
What's that?
What do the Americans call them?
We call it a exponent. Exponent index. Power. Index law. The text we use is Australian, so they often use the British versions of words, which is hilarious. Alright, so here's the same idea. If you have like a bunch of 2's up here, and some 2's down here, let's add one more in there, and some 2's down here, you're pretty confident with like being able to say, hey, that's 1, that's another 1, that's another 1, and scratch those out, right? And so if you thought of this as you're left with just 2 2's. So if you had 2 to the 5th, that's 2 to the 5th, and this is 2 to the 3rd, you're really subtracting the ones that are redundant, giving you 1. And so you can subtract these 2 and call this 2 to the 5 minus 3, which is 2 to the 2, just like you expected, right? Now, I think you've probably seen that before, but this is the generic version of that. Yeah?
What if the denominator is bigger than the
Cool. So let's try it. Hey, it worked! Sweet. Great. So if you did that, like that, you're left with 2 down there. I like you thinking. So there's our 3. There's our 5. You'd subtract them in the opposite order. 3 minus 5, you get negative 2. For now, we'll leave it like that. Tomorrow, no, maybe it's today. I'll show you how to like visualize what that is. Cool? So for now, you can leave it. You could also think about it as, well, yeah, we'll get there in a second. So that 7 to the 8 over 7 to the 5 is 7 to the 8 minus 5, so 7 cubed, which is, no one cares, 7 cubed, right? Try that with this one. B to the M. Alright, so hopefully that one was same base. If they're different bases, you can't play the game, right? Because if this is B to the 6th over C to the 2, making stuff up, this is a bunch of B's over a bunch of C's. And this doesn't make 1 when you cancel it out, right? It's like 2 over 3. That's not 1. It has to be 2 over 2 to make 1, or 3 over 3 to make 1. So they have to have the same bases. They don't have the same bases, you can't play the game. Don't you want to play the game, coach? Chief, sorry. B, so B6 minus M. Do I know what M is? No. So that simplifies to, it doesn't. You have to leave it like that. Neat? Great. Shazam. Okay. Last? Maybe not. Last maybe not. Let's hope. So index law number 3. Right there. Shazam. Power to a power. Grab your SpongeBob.
How many of these are there?
14. No. There's like these 3, and then like a couple other little tweaks, but like I would say there's 5. Yeah. So this is like if you have, I don't know, I'll give you an example like 2 cubed. Let's do it with x's. X cubed. Right? This is a power, and then you have a power of that. That's gross. But all that means is I have x cubed times itself twice. This is really 3 x's all multiplied together. And that's really 3 x's all multiplied together. And so I have 2 sets of 3x. So instead of like breaking it up and adding them up, you just say, hey, multiply those 2. Because I have 3 x's here, and I have 2 sets of 3x. That's multiplication. So really you can call this x to the 2 times 3, which is x to the 6th. Unsurprising, right? But again, individually, they make a lot of sense. But when you're like moving through the mathematics, it gets sticky, right? You're like, which one do I do? Do I add? Do I multiply? So this is really 3 sets of 4 2's. So it's like 2, 2, 2, 2 times 2, 2, 2, 2. You get the picture, right? There's 4 more over there. So instead of doing that, which will always work, right? Call it that. So 2 to the 12th, which is no one cares, right? 2 to the 12th, right? I don't need to see you multiply big numbers. You try it. Shazangle and shazangle.
Really, one question.
Yeah.
How is it?
Cool. Think about it if it was like 2 to the 4 and just regular square. This would be 4 sets of 2's and 2 sets of all of that. So I think that's 8. This is 2 to the 8. And you got that from 4 times 2. If this is negative, you do the same thing, but you multiply. So this is going to be positive 8. You're going to deal with it and you accept it. It's good for 4 seconds. Alright, so that's x to the what? 15? And that's b to the 7m. I don't know what m is, so we just got to move on. Neat? Okay, grab your calculators and try this. Type in 3 to the 0, type in 5 to the 0, type in 17 to the 0. What? So whack. So 3 to the 0, that equals,
1.
okay. And 5 to the 0, that,
1.
what? And then, 17 to the 0. Wait, how about 206 to the 0?
1.
You guys are pulling one over. How about pi? Take that, pi to the 0.
1.
Shut my mouth. Should we just... So, it looks like anything to the 0th power is 1. Except for 0. Yeah, that's weird. But, try it. Your calculator explode. That's the one little glitch. And we'll talk about that later. But, anything to the 0 power is 1. So, maybe write that down. Like, x to the 0. What? It's our index law number 4 out of 15. Let me show you. I don't want you to take it on blind faith. Mr. G's TI-84 Plus Silver Edition told me so. Let me show you why.
Yeah, because we had this question in an assessment in 8th grade, and they asked us to explain why it happened.
There's a couple of ways to explain it. This is the one that I like the best. There's 2 ways that I like. So maybe build me a little list like this. We're going to use this list to figure out about negative exponents in a second too. But start with the 2. 2 to the first is 2. 2 squared is 4. And 8. 2, 4, 8. Yep. And then this must be 16. Give me that list. You can try it with 3s if you want. 3, 9, 27. On the left-hand side, what you'll notice is we're decreasing by the exponent by 1. So the exponent goes down by 1. Right? Same thing, goes down by 1, goes down by 1. Goes down by 1. What happens to get from 16 to 8?
Divide by 2.
Divide by 2, yes. Divide by 2, right? Drop the exponent by 1, go from 8 to 4. Hey, same pattern, divide by 2. Drop the exponent by 1. Hey, divide by 2. Drop the exponent by 1, divide by 2, which means you get 1, right? Play that same game here. Drop the exponent by 1, divide by 2. 3, right? 3 is the base. We're changing by 3 each time. So we're dividing by 3. Drop the exponent by 1, divide by 3. Drop the exponent by 1, divide by 3. Bam. Patterns, right? And so that's one of that's one way to see it, is that pattern. Here's another way to see it. Shazam. Is with what you already know about dividing, right? Any number to the 0 power equals 1, except 0, which is kind of weird. But let me show you the second. This is a little more algebraic way to visualize it. Case number 1. Any number divided by itself is 1. You take 5 pizzas, you put them in 5 piles. Every pile has 1 pizza. Right? That's not surprising. So if we did something like this, 4 cubed over 4 cubed, that's what, 64 over 64? That should be 1. Yeah? So that's fine. Also, we know that if you have exponents, same base, you can subtract them, right? I got 5 2s and 3 2s. I can subtract them and make 2 2s. Not that kind of 2 2s. If we played that same game with this, like this, if we called this 3 cubed and 3 cubed, here you subtracted those. What would you do with this?
3 minus 3.
Yeah, you go 3 minus 3. You get 4 to the 0. And so, if all of this stuff equals 4 to the 0, and all of the same stuff equals 1, what can you say about 4 to the 0 and 1?
It's the same.
They're the same, right? We started with this. Fundamentally, this is 1. Also, fundamentally, this is 4 to the 0. They got to be the same, right? An algebraic, not quite proof, but indication. Cool? So, here's mine. 7 to the 0. This one. This one. There we go. Here's yours. Alex, what's up? Oh, they want
The most of the camera, it's like,
It's neat. Because you're that's quite funny. I can draw really straight lines with my fingers and
What?
Alright, guys, let's try this out. So, x to the 0, surprise, 1. This is 4 over y to the 4th and y to the 4th, surprise, 1. This is 2 plus 5 to the 0, 5 to the 0 is 1, so 3. Not bad, not bad, not bad. Not so simple. Okay, that's great. Let's rock with a couple of these. I want to be able to take all those laws and just kind of smush them together and see what we can do with them. So I'm going to try to just simplify that, make it look prettier. Everything there is being multiplied. So sometimes it helps me to stop writing them in little chunks if I see that it's multiplied and write it like this. 3 times x squared times 5 times x squared. We can use the commutative property of multiplication, which means that like you can multiply in any order you want. 2 times 3 is the same as 3 times 2. 6, right? So instead of multiplying this, then this, then this, then this, let's put all the numbers together, the constants, and go 3 times 5, and then the exponents. Right, that's 15, and then you would multiply those together. No, you'd add them, right? X and X and X and X, so you get, I guess you get the same thing, right? Voila.
Did you put the power as 2? The power is 5.
Mother of pearl. Thanks. Transposition error. Cool, so 10.
What? 7.
I was gonna do this. Cool, okay. It's got 2 x's, 5 more x's, 7 x's. Leave it alone. You try these. Shazam, Shazam. Think about what's really there. Think about using those index laws. Cut them apart. I'll work through them with you in a second.
It's 28 days in
Oh.
There's 28 days in February. Oh.
So that's gross, but let's try it out. So this is 20 and a to the 9 over 4 and a to the 6. Sometimes it helps to visualize, if you're multiplying like this, to break it up into 20 over 4 times a to the 9 over a to the 6, if you like. That's 5. That's, what you subtract those, so a cubed. Something like that. This one, oh, that's gross. DVD. Move it over, you. I don't know. I might switch the top and bottom first and call this 10 B's up there, 8 B's down there. So subtract, you get 2 B's? Or not 2 B's? Express, prime. No. Maybe. I'll do one. I'll do for simplest prime number base. That's not a prime number base. It's 4. We can break that apart. So really this is 4 is really 2 squared to the 4th.
What? No.
Yeah.
Right? This 4 is 2 to the 4th. This 4 is 2 squared.
Yeah.
That's fine. And then really, like, these I can multiply. I have 4 sets of 2 2s. So I get 2 to the 8. Yeah. Bing. Ooh, that's actually a good one. You try that one. Turn the 9 into 3s. And then switch the 3s.
I don't get it. Get it? Wait, it's 3.
So 9 is really 3s in disguise. How many of them? 2 of them.
3.
And there's 8 of them. So if I have 2 sets of 3, I've got 2 3s and a bunch more. I would just kind of add those two up. So this turns into 3, 2 plus A. Yeah? Great. Let's keep moving. Ping! More tricks like this. Here's mine. I have 3A squared, which really means 3A times itself. If you're ever in doubt, just write it out. That's kind of right, though. And then you can rearrange the numbers, right? Like I've got 3 times 3 and A times A, and so I've really got 9A squared. You can sort of think about it distributing in like that. There's a little danger, though, if you think about this. If this does not work, let's do this. 3 times 2 squared, that's 6 squared, that's 36. Totally works with multiplication like this and this. You get 9 and 4, still 36, right? It works. What doesn't work is if you have 3 plus 2 squared. Should be 5, should be 25. Yeah? If you do this, ka-ching, ka-ching, you get 9, you get 4, not 25, right? So this only works, this distribution kind of shortcut visual only works if you have multiplication. I can't tell you how many of my seniors got toasted for that on their mock exam. Oh, P.S. I've got a great exam problem that used law of cosines on my seniors mock exam that you guys could do. It's pretty sweet. I was working through it. I was like, wait, did we just do this in 9th grade? We got it wrong, too, losers. All right. You try that one. When in doubt, write it out. Wow. Okay, so 2x over y cubed means 2x over y times itself 3 times. when you're multiplying fractions, like a half times a 3/4, you multiply everything on top and everything on the bottom. We're just going to do the same thing here. Multiplying the 2 and the x and the 2 and the x. I broke it up with a bunch of dots. It helps me visualize how to recombine things. You don't necessarily need to do it. It's an art form, right? So find your own flow. I have 2 cubed, which is 8, x cubed, and y cubed. Right? Maybe you want to call this one 8. So basically, it looks like you can shortcut it and go ba-boom, ba-boom, ba-boom. 2 cubed is 8, x cubed is x cubed, and y cubed. Cool. But again, this breaking it up like this will make things a lot easier, even if you're just doing it visually and sort of imagining it broken up. It'll help you avoid some pitfalls, I think. No. Here, there's that. It's on the video if you want to see it. Ba-bam, ba-bam. But again, we'll break it up. I want to get to the good stuff. This is the good stuff. Bum, bum, bum. We already did the 0 exponent. We already did the 0 exponent law, right? X to the 0 is 1. We got one last one, which is what Nick was looking at. It's like, what happens if you have a negative exponent there? You can leave negative exponents, but also sometimes it's easier to manipulate it if it's not negative. So I'm going to do this again. Just add to yours. This was 16, this was 8, this was 2. No, 4. This was 2. This was 1. Extend the pattern, right? I'm dropping an exponent by 1 each time. I'm subtracting an exponent. So 2 to the 0 becomes 2 to the negative 1, then negative 2, then negative 3, etc. That's fine. So, and we saw that every time we drop by 1 on the exponent, we're dividing by 2. We're dividing by the base, maybe more accurately. So this one's not bad. When you drop another exponent, we should divide by 2. So what should you get here? Yeah, and I'm going to write it in a specific way. I'm going to write it as 1 over 2 to the 1.
What?
1 over 2 to the 1 half. Not a big deal. I'm just going to write it like that for a second. If we drop again by 1, what do we do with the half? Divide by 2. If you take half a pizza and you divide that in half, what fraction of a pizza you get? 1/4. So this should be 1/4. I'm going to rewrite it, though. I'm going to call it not 1/4, but 1 over 2 squared. If we play the same game again, we take our 8, I almost gave it away. If we take our quarter pizza and we divide it in 2, what's a quarter cut in half? An 8. Yeah. And so instead of writing it as an 8, I might write it as 1 over 2 cubed, 2, 4, 8. You see what I'm getting at?
Yeah.
What do you think 2 to the negative 4th is going to be?
1/16.
Yeah, it's going to be 1/16, otherwise known as 1 over 2 to the 4. Right? This is the negative exponent law, which says like x to the negative n really should be what? See,
1 over x to n.
Yeah, 1 over x to the positive n. That's our last exponent law, right? Now, why would you do that? Well, maybe you don't want negative numbers. Switch it to fractions. Maybe you hate fractions. Switch it to negative numbers, right? It's a tool that lets you flex back and forth between those two. Cool? That's index law number 5. Next.
Okay.
You can also do that with the 3s if you want to see it, but so here's, I'm going to use that idea. Here's this one. I don't want to like build that whole list each time. I just want to use this understanding that this is kind of like a little elevator button. And so 2 to the negative 2 should be, this negative says 1 over, and then all of this stuff is in the denominator, right? So the negative is just a 1 over, and this is left over, 2 squared, so 1 over 4. You try these things. No. Ooh, that was good. Oh, don't worry about 5 to the 0. He's just playing.
Should we leave it as a 2 square or 4?
If you can do it on your fingers, turn it into the 4.
Yeah.
2, 4, 8, 16, 32, 64. I'm out of fingers. I only got 6. Use your best judgment. I don't need to see you be a calculator, but I do need to see you fight with these index laws. Right.
1 minus 5 to the minus 1.
What? 1 to the 5 to the minus 1?
H to the is a... so this is 5 to the 0, so that's 1. This is minus. I'm going to look at that thing. 5 to the negative 1 should be 1 over 5 to the positive 1, which is just 1 over 5. So this is 1 minus a fifth, so it's 5/5 minus a fifth, so it's 4/5. Voila!
No.
Ooh. 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 This one's a good one. This one's a good one. So this -2, might take this -2. This one's really gross, so you'll have to follow me on it. So this is 2 to the -2 and 5 to the -2, right? I'm sort of doing that distribution in there. Because if it was 2 over 5 and to the positive 2, it would mean you'd have 2 of them multiplied together, and so I'd have 2 squared and 2 5s, right? It's -2, so I have -2 exponent for that and that. So I think that's okay. The fussy bit, I might break this up so you can see what's actually happening. I might call this 2 to the -2 times 1 over 5 to the -2. You don't have to break it up like this every time, but I just want to show you what's physically happening, what's mathematically happening. This one's easy enough. This is 1 over 2 squared. But this elevator button, drag the 2 squared kicking and screaming into the denominator. What do you think this elevator button is going to do?
Same thing.
More down?
Yeah.
Just like 2 denominators. It kind of does. It kind of does, yeah. It just switches that place, right? You're doing the same thing. If you're saying 1 divided by, that's actually spot on, Charlie. You are brilliant. If you're saying 1 over 5 squared, when you divide fractions, you take this first one and you invert and multiply that second one. Okay, that's how we multiply fractions. You say like 1/2 divided by 2/3. You would keep this. You'd multiply by this thing flipped over. So you've heard that as what keep flip something something.
Flip chain.
That's the one, yeah, nobody remembers that.
Yes,
Right, so that same thing, this turned into just straight up 5 squared over 1. So this dragged this piece up to the numerator, 5 squared over 1. And so that negative in the denominator did that. The negative just flips where it is in the fraction. It's in the bottom and negative, goes up. It's in the numerator and negative goes down. Cool. So then this turns into 5 squared over 2 squared, which is 25 over 4. Do you want to see another one like that?
Yeah.
Yeah.
Wait. What
This
does
used to
it
be a
mean?
long time ago.
Let's do another one that's similar. All right. Let's try one that's similar. Just walk through it again. Like, let's go 3/4 to the -2. The short way that eventually you'll do it is this. This distributes into here and here. This turns into 3 to the -2, 4 to the -2. This negative drags the 3 squared to the bottom and makes it positive. This negative drags the 4 squared to the top and positive. Right? Done. That's the shortcut. Like, that's what I want you to do eventually. Numerically, what's happening is this.
Wait, no?
You need that back? Sorry, I get you. So that's the shortcut, distribute, because really you have it. And then the negatives switch places. Right? This comes up to the top and is positive. This goes down to the bottom as negative. But this is physically why that's happening. You get 3 to the negative 2 over 4 to the negative 2. This is really 3 to the negative 2 times 1 over 4 to the negative 2. This plays the game that we kind of just saw the pattern of, which is 1 over 3 squared. This does this, and then the 3 squared's down there. And then this, I'm just going to put a little aside, 1 over 4 to the negative 2. I'm going to play that exact same game. This is 1 over 4 to the negative 2 becomes 1 over 4 to the 2. This negative is this piece. When you divide by a fraction, you'd say this numerator, 1, divided by 1 over 4 squared, let's just call it 16, cut to the chase. So 1 over 16. When you divide by a fraction, you keep the first one and you multiply by the reciprocal of the second. Actually, I might leave it as 4 squared. Just because it'll be easier to see. So 1 times 4 squared over 1 is just 4 squared over 1. So I'm going to write it like that. It helps me see that this flips over, and this flips over too. Right? And so then these you can combine and just call it 4 squared over 3 squared. 16 over 9. Simplify through. Cool. Like, individually, like, everything makes sense. And then when you start compiling, you're like, oh, wait, what's happening there? And, like, walking through, like, things that you already know. You know that you invert and multiply when you divide fractions. But all of those things start coming together. And you're like, what you got to keep track of all of it. And that's challenging.
In the assessment, you trick all this out?
No. No. I want you to go from here. I would probably go that, and then that.
Okay.
Yeah? That's the short version. But this is like, this is all the tricks behind it, and I want you to see that we're not making stuff up. It works with the things that you already know, and there's shortcuts for all of it. But then when I'm moving fast and I'm doing like trig and calculus and this and that, like does that work? And I go back to something basic and try it. Cool. Ba-boom. Do C. Try C. Try C. Yeah, great. The boom, so you multiply those, they become negative, so the whole thing drops to the denominator. And so this becomes 1 over 2 to the 8.
Do you have any more math books?
I might. We bought enough to get you the first one for free. The second one you have to sacrifice a calculator.
I don't know. I won't be left. Oh, don't get so that is just what? What?
So if this was like 3b squared, you'd have 2 sets of the 3, and you'd have 2 sets of the b squared. Since it's negative, we do the same thing, we just keep the negative. So this really becomes 1 over 3 squared, and this becomes 1 over b squared squared. A couple of different ways to visualize it, but this is just kind of how I want you to eventually roll through it. So this is 1/9, and this is 1 over b to the 4th. And so you can recompress them into 1 over 9 b to the 4th. Turn the board.
Okay.
Which part? Are you okay that this does this?
Yep.
And this does this, and all of this part, like just like all of this part drop to the denominator. All of this part drops to the denominator too. And then I have two sets of 2, so 4. Cool. Again, like individually, all the pieces make sense, but then once you start compressing them.
Can you go back to one of the previous ones?
Yeah.
No, the ones next to that one.
That's a good one. That's actually a good example. So this is 5x to the -1. It means the whole thing is to the -1 and it drops that down. But if you have 5 times x to the -1, it's just the x to the power. So just be careful. Cool. I think that might be all the time we have. We're going to do A and B. There's a lot there, but the next section, there'll be a lot less. So try to do like every third one or something like that. Oh, you have beautiful booklets. Here they come. We're so excited. Alice is so excited about the booklets. Full color, full Technicolor. Yeah, baby. So good. Leo's been waiting for this moment. So glad we made it. Look how far we come. How'd it go? Yeah. Ciao, chicos. Good to see you.